23B, the sample average. Number 1, match each phrase from A to B. The population would be the box. The population average would be the average of the box. And we call those parameters. And parameters are often very difficult or impossible to create. The sample would be the draws. The sample average, average of the draws, and the sample size is the number of draws. Okay? And samples create statistics. And my favorite example, and this was in one of my statistics classes, my professor pointed it out. Sometimes it's totally unethical to create a parameter. And my favorite example is blood tests. Right? They're not going to drain all your blood into a bathtub and then test it, because it's not going to do you any good. So they just take a sample. Well, is that sample going to exactly replicate the true percentage of your blood? No, but it should be close. Our blood is pretty well mixed. So whenever you get a test, doctors tell you, oh, hey, you're good or you're not good. Well, that number they get has an error associated with it. And the lab people know the errors, and the doctors might even know the errors, but they never tell you what it is, ever. They just treat the number as though it's fact. All right, number 4. In example 3 on page 417, suppose 50 different survey organizations take simple random samples of 400 persons aged 25 and over in the town. Each organization gets a 95% confidence interval, sample average plus or minus 2 SEs. How many of these intervals should cover the population average? So I don't even need to turn back and look at it. What it's saying is, if this is my true average of the box, then 50 people are going to go out and create a sample. If they do everything correctly, then they will create a confidence interval, and the goal is that the true average will lie somewhere between the low and high end of their confidence interval, right? And lots of people are going to do this, and some of the people will be wrong. How many of them do we expect to be wrong? Well, 50 people did the survey, and our confidence interval is 95%, so 95% of 50 would be 47.5, but that doesn't make any sense because these are people. So even a short person is a person. I know it's hard to believe. So 48. We would expect 48 out of 50 of the people to be correct, and 2 of them, about 2, we would expect to miss. Now, if 4 people missed, would we think that that is shocking? No. If everybody was right, would we find that shocking? No. But if 10 people missed, we would think, man, that's way off. So that's another thing that we're going to deal with eventually. How many people can be wrong before we start to get worried? And guess what the answer is? You get to decide. Just like you get to decide, I want to be 95% confident, or I want to be 90% confident, or 99% confident. You also get to decide, how far off can I be before I start to worry that something wrong is happening? We'll get to that. Not in this chapter. Okay. Number 5. The figure below is a computer simulation of the study described in exercise 4. The confidence intervals are plotted on different heights so they can be seen. A, why do the intervals have different centers? True, chance variation. What does the center of each interval represent? the average of that particular sample. So it's saying that the sample averages are different, which we expect. Okay. B, why do they have different lengths? Yeah, the SDs are different, but wait a minute. We're only calculating one number, right? We run out and we do a survey and it says, so we're talking to 400 people, and let's say I get a sample average of 38%, and you get a sample average of 42%. Shouldn't our SDs be the same? They're not. Why not? But we both talk to the same number of people. Well, the SD is dependent on the sample average. So watch this. The square root of 0.38 times the square root of not square root, how about just times 0.62, and then the square root of 0.42 times 0.58. Why does this one have a bigger SD? Because it's closer to 50%, right? If the sample average is 0.5, then in the box we have 0.51s and 0.50s, and the SD is 0.5, right? Well, what if we had 0.1 and 0.9? That's going to be pretty close to 1. Or sorry. So if I did the square root of 0.1 times 0.9, I end up with an SD of 0.3. Because most of my tickets are zeros. Right? I have a few ones, and I have lots of zeros. So the width of a confidence interval is based on the number of draws, but it's also based on the sample percentage, which means sample percentages that are very small will create narrower confidence intervals than sample percentages that are high or close to 50%, which is weird, right? We are more confident that we're correct when the sample percentage is close to 0. Anybody else find that strange? I mean, you never would have thought about that. You probably would assume that they're going to be the same size because the number of draws. But if your sample percentages are close to 1/2, we are less sure about how accurate we are going to be. And your confidence intervals end up being wider, even though you talk to the same number of people. Okay, see, how many of them cover the population average? So basically, we're going to count the number that missed. How many missed? Just one of them, right? So 49 out of 50 covered. How many did we expect? We expected 2 of them to miss, and we got 1 of them. Are the alarm bells ringing? No, that's close enough. Okay, number 6. A university has 30,000 registered students. As part of the survey, 900 of these students are chosen at random. The average age of the sample students turns out to be 22.3 years with an SD of 4.5. The average of all 30,000 students is estimated at 22.3. The estimate is likely to be off by 4.5 or so. Find a 95% confidence interval. So my survey yielded 22.3 plus or minus 4.5. So my confidence interval, 22.3 minus 9, and 22.3 plus 9. Now, did the book list it like this, or did they just put plus or minus 9? Anybody check? So this is number 6B. Did they say 22.3 plus or minus 9, or did they say 13.3 to 31.3? Oh, how nice is that? Okay. Oh, sorry. So this is wrong. That's the SD. Thank you. 4.5 is the SD. So we need to do, I'm glad you caught that, divided by the square root of 900, which is 30. Turn that into a decimal. So 15%? Okay, which means this is 30. Sorry, it said SD and I thought SE. Okay, that's not very accurate, right? I'm 95% confident that the true percentage is somewhere between negative, what would that be? 7.7 and 52.3. Great. I'm 95% confident that's going to happen. Okay. All right. And, oh, that's it.